Hello and welcome to Unit 9. In this unit, we will start to think about relativistic dynamics, momentum, and energy. So far this course has focused on kinematics, which really is just the description of motion. How to describe motion and events in different reference frames, what's the same and what's different in different reference frames. But we haven't talked about dynamics, why objects move and how interactions might change an object's motion. So in this unit, which is the last unit of the course, we'll take a first step, an initial look at relativistic dynamics, building towards the famous equation E equals mc squared. So our starting point will be to think about momentum. So momentum in classical physics is defined as m times v, an object's mass times its velocity. And the velocity is taken to be a vector, which means that it's moving through three-dimensional space. And we would need to think about the three different components of that velocity, how fast it's moving in, say, the x direction, the y direction, and the z direction. So momentum is important because momentum is conserved, which means that if you have a closed system, the momentum of that system won't change. So you might have two objects, maybe these two lacrosse balls, and they may interact. So here we have this situation, but then we have a little collision, and then after the collision, maybe it goes like this. And lots of different collisions are possible. You could have something that goes like this, many different things. But in all of those collisions, momentum is conserved. What that means is if you add up the momenta of the objects before the collision, you'll get a certain number. You'll add up the momenta of the objects after the collision, you'll get the same number. The individual momentums might change, but the total momentum of the system will stay the same. And that's a bedrock principle of classical physics, that that momentum is conserved. And you can show that it's directly related to Newton's second law, F equals ma. Okay, so here's the problem. In special relativity, conservation of momentum no longer holds, or conservation of momentum using the classical momentum formula, mv for momentum. So maybe we have a collision like this. There is a ball at rest, one comes in, the ball goes off. That would conserve momentum. Momentum would be the same. But if we had Anastasia view the same thing, moving along in a significant fraction of the speed of light, she would see different velocities for all three of the balls. And we could calculate what those velocities are using the Einstein velocity transformations that we covered in the last unit. And if Anastasia were to do that and calculate the momentas before the collision and then after, she would find that momentum is not conserved, that number has changed. So this is a calamitous state of affairs for physics. Again, momentum is a bedrock principle of physics, and the fact that classical momentum is not conserved in special relativity suggests that something is very wrong. It suggests that we have to redefine momentum in the context of special relativity. So that's what this unit will be about. In the next video, we'll start thinking about momentum, and as we often do, we'll begin by thinking about space, x, y, z, and then we'll expand to consider space-time, x, y, z, and t.